Hi, welcome to engineering chemistry. And the course has been divided into four parts. So we have part one, part two, part three, and part four. So for part one, we're going to be looking at the atoms, atomic mass, elements, and periodic table. Then from there, we go to chemical bonds, redox reaction, and then chemical equilibrium. So for lecture one, we're going to start with atomic composition. We all know that atoms are made up of protons, electrons, and the neutrons. So the protons are the positive charge, positive electrical charge. The electrons are the negative electrical charge, and the neutrons are they have no charge. So if you look at the figure on the side, you see that the protons and the neutrons are the one inside the nucleus, while the electrons revolve around the nucleus. This position is very important as we're going to be talking about how they're going to react according to this position in later in the lecture. So you have to note that the composition of the nucleus of an atom are the proton and the neutron, while the electron revolves around the nucleus itself. So when you pick up a periodic table, you're going to see something like this. And the basic thing that you have to know on each symbol are the atomic mass, the elemental symbol, and the atomic number. So for example, for this case, you see that we're having the elemental symbol, which is the aluminium, that has an atomic number of 13 and the atomic mass of 26. So all atoms of the same elements will have the same number of protons in their nucleus. You see, we are always emphasizing the position of protons in the nucleus, that it's always in the nucleus. So atomic number don't change. Atomic mass can change. It depends on the number of the neutrons that the element has, which we're going to talk about later. Then we move to atomic mass. Atomic mass is the number of protons and plus the number of neutrons. As you can see, you see that basically atomic mass will be what is inside the nucleus of the atom. Remember, inside the nucleus of the atom, we have protons and we have neutrons. So when you add the two together, it gives you the atomic mass. For example, we have carbon 12 that has 6 protons and 6 neutrons. So if you add them together, it's going to give you 12. And that's why it's called carbon 12. So carbon 12 has atomic mass of 12. However, we also have another carbon, which is called carbon 13. It has atomic mass of 13. And how does that happen? It shows that, remember, the protons of an atom don't change, like I said earlier. So the protons remain 6, but the neutrons for carbon 13 is now 7. So if you add the neutrons and the protons, which is 6 plus 7, it gives you 13. So that's why we have carbon 12 and carbon 13. So don't be surprised we have elements like this. And this kind of elements are what we refer to as isotopes. So the elements with different number of neutrons, they are called isotopes. So isotopes have the same number, the same atomic number, but they have different atomic masses. So another example, apart from carbon, is hydrogen. Hydrogen has 3 isotopes. You can see the first isotope has 1 neutron, but 1 proton, beg your pardon, but 0 neutrons. And that's why you have it as 1, 1, and the name is protium. So the second one has 1 proton and 1 neutron, which is called deuterium. And as you can see, if you add the two together, it makes it 2. So the atomic mass is 2, while the atomic number is 1. So For the last one has 1 proton and 2 neutrons. That's why we're going to have atomic mass of 3. And then the atomic number remains the same, 1. And the name is tritium, beg your pardon, the name is tritium. Let's quickly do some learning check. So we identify which statements describe the following: the proton, the neutron, and the electron. So for A, it said found outside the nucleus. Remember our first slide. So which of these can be found outside the nucleus? The position, we're talking about position now. The second one, B, says has a positive charge. Which of these also have a positive charge? The third one, C, said it's neutral. So if you go to those slides, then you should be able to answer these questions. The last one said it's found in the nucleus. Remember, you can find 2 things in the nucleus actually. So which of these can be found in the nucleus? So the summary of it all. So protons, in terms of charge, is positive. Neutrons the neutrons have no charge, while the electrons, they are negatively charged. Their location: protons are found in the nucleus. Neutrons are found also in the nucleus, but the electrons, they are outside the shell, they are outside the nucleus. They are revolving around the nucleus. So in terms of mass, proton has 1 atomic mass unit, neutrons 1 atomic mass unit, while electrons is 2,000 times smaller than the proton. And what do they do? Their job. So proton determines the identity of the element. Like I said, protons don't change. The number of protons don't change. So they are so unique to that particular element, and they determine the identity of the element. The neutrons, they supply a proper mass to hold the nucleus together, because if you have just the positive charge and their masses and there's nothing to balance them together, then it's going to, so they basically supply the mass to balance the nucleus, to hold the nucleus together. So, and electrons determine the bonding, how it reacts. We're going to get to that later. Because the electrons, they're outside the nucleus and they are the one revolving around the nucleus. So they are the one that these elements will use to react with another element. They are, in terms of number, protons equals to the atomic number. So when you have the atomic number, that's also the number of protons. But for the number of neutrons, it is atomic mass minus the atomic number. That's what's going to give you the neutrons. Take note of that. When you subtract, your atomic mass, you subtract atomic number from your atomic mass, then you're going to have the number of neutrons. For electrons, they have the same number of, they are the same as the number of protons, but we have some exceptions. If that particular atom is in a charged state, then the number of electrons have been affected. So it's not going to be the same as the number of proton when they're in a charged state. But when they're just in a normal state, in a ground state, the number of protons is equal to the number of electrons. So for your library work, I want you to find more examples of atoms that exhibit isotopy. More examples, we've discussed carbon and hydrogen. So I want you to find more examples of atoms that exhibit this phenomenon called isotopy. So we move to elements and the periodic table. Elements and the periodic table. So the periodic table itself, modern periodic table, was developed by a Russian scientist called Dmitry Mendeleev. So this man argued that elemental properties are periodic function of atomic weights. However, from the latest research that we have, the latest research shows that that's not right, that the element properties are periodic function of atomic numbers, not atomic weight. Like I have said earlier, that atomic number is unique to each element, and that makes it a determinant to the property of that particular element. So this is the periodic table, blank. This is how it looks. Periodic table has features such as the blocks, the period, the groups, and so on and so forth. So for this one, you can see that the arrow going down, the arrow which is the horizontal, is the group. So when it goes vertical, it's the period. So for this particular one, we can see that the periodic table is also divided into blocks. We have S block, we have D block, and we have the P blocks. So for groups, groups are the one from the previous slide, they are the one that goes, they are the horizontal ones. So for groups on the periodic table, we're only going to look at the group A, the group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. We have other groups in between. These groups are called the transitional elements, as you can see. So transitional elements are the elements that are in between the group 2A and group 3A. As you can see also on this particular slide, you can see that those groups have unique names. Not all of them, but you can see that group 1A is called alkali metals. Group 2A is called alkaline earth metals. Group 3, they don't have common names. We'll get to that later, why they don't have common names. So for group 7A, they're called halogens, and group 8A are called the noble gases. Okay, we also have regions on the periodic table. So we have the main group metals, we have transitional metals, which I've already told you earlier, they're in between group 2A and group 3A. We have metalloids. Metalloids are semi-metal, meaning that they are somehow in between metals and non-metals. Then we also have non-metals. So the elements that fall into this particular region, they are, okay, you're going to define them based on the region that they fall into. If it is metalloid or non-metal, or the main group metal, or the transitional metals. All right, for group 1A. Okay, before I go into detail, let me just cheat this in that the reason why they are called a group 1 is because they have one electron in their outermost shell. They have one electron in their outermost shell. So if you write the electronic configuration out, you're going to discover that all of them that belong to that group actually have one electron in their outermost shell. And that is why sometimes for this group, they include hydrogen for this group because hydrogen has just one electron. But technically, hydrogen does not belong to this group because hydrogen is not a metal. So for group 1A, they are known as alkali metals, and they are lithium, sodium, potassium, rubidium, and cesium. I think we also have francium in that group as well. So these elements, they are the leftmost column, group 1A, and all the alkali metals are solid at room temperature. You have to note that. So they are all solid at room temperature and are all reactive with water to produce hydrogen and basic solutions. So they were all going to react with water. So these elements are only found in nature combined in compounds. So for example, we have sodium chloride. They are never in free state because they are very reactive. So they're not going to be a free element. They must have reacted with something. For example, sodium reacted with chlorine to give you sodium chloride, which is what we call the table salt or called common salt. So for group 2A are called alkaline earth metals, and they are beryllium, magnesium, calcium, strontium, barium, and radium. So these groups are in the periodic table group 2A, and it's also composed entirely of metals that occur naturally only in compounds. So they are also, all of them are metals and they occur naturally in compounds. That means they too must have reacted with something. So except for beryllium, this element reacts with water to produce basic solution. So except for beryllium, every other element that belong to that group, they they can react with water to produce basic solution. So again, we also have some of them that are in form of oxide. For example, we have calcium oxide. So if you dissolve calcium oxide, also known as lime, it's going to give you an alkaline solution. And that's why they are called alkaline earth metals. So we have magnesium and calcium. They are the seventh and fifth most abundant elements in the earth crust, respectively. So for group 3A, we have boron, aluminium, we have gallium, indium, and thallium. So not all of them are metals, and that's why they don't have, like I said, they don't have a common name for them because we have they comprise metal and non-metals. And metalloid, beg your pardon. So boron is the non-metal. The rest, aluminium, gallium, indium, and thallium, they are all metals, but boron is non-metals. So aluminium, it's the most abundant metal in the earth crust at 8.2% by mass. It is exceeded in abundance only by non-metal like oxygen and metalloid silicon. So, but for metal is the most abundant. Then we also have, so funny that we also have gallium, which is one of the few metals that can be liquid close to room temperature. So gallium, can turn to liquid close to room temperature. That's the figure this side. Group 4, we have carbon, silicon, germanium, tin, and lead. Again, group 4 comprise, this is also very interesting because now group 4 has non-metal, metalloids, and metal in the same group. And that's why they don't have common name. How are we going to name such a group? They don't have common name. So for the non-metal, we have carbon. For metalloids, we have silicon and germanium. And the metals, they are tin and lead. So because of the change from non-metallic to metallic behavior, more variation occurs in the properties of the elements of this group than most others. So because of these unique properties where they have everything in the same group, their properties are they are in various forms. They are called in various in diverse properties. For example, you can see the diagram here is diamond, which is a form of carbon. Carbon also can exist as graphite. We also have graphite, which is also a form of carbon. Well, despite the fact that they are all different, we have non-metal, metalloids, and metals, they still have something in common. So, for example, these elements they form compounds with analogous formulas such as CO2, SiO2, GO2, and PbO2. So they have that in common. You can mostly see them as this kind of analogous. Group 5A comprise nitrogen, phosphorus, arsenic, antimony, and bismuth. So nitrogen in group 5A occurs naturally in form of diatomic molecules, N2. So we're going to talk about the elements that are mostly in diatomic or polyatomic molecules later. So it makes up about 3/4 of the Earth's atmosphere. Then there is another precious example, which is phosphorus. Phosphorus is essential to life. It is an important constituent of the bones, the teeth, and even in our DNA. So the element glows in the dark if it is in the air, and its name is based on the Greek word meaning light bearing, and that's representative of phosphorus picture, representative picture of phosphorus. So you can see we have it as red phosphorus. We also have it being white, also phosphorus. So for polyatomic that I mentioned earlier, so we have some elements that are just, they occur as polyatomic. And these are the examples. We have hydrogen, nitrogen, oxygen. Oxygen has two. We have O2, we have O3. We have F2, Cl2, Br2, and I2. So when you speak, for example, when you speak of oxygen in its natural state, you are referring to O2. So when you say, oh, I breathe in oxygen, you are not breathing in atomic oxygen, but you are breathing in O2, that's oxygen. O2. So when you talk about them in their natural states, they occur in that form. So for this kind of chemistry, it's just something that you have to master. So you have to know which of these elements exhibit as polyatomic, and you have to know the number that they exhibit. So for group 6A, we have oxygen, we have sulfur, selenium, we have tellurium, and polonium. So oxygen, which constitute about 20% of Earth's atmosphere and which combine readily with most other elements. So is at the top of the group 6A. So oxygen is very important. So most of the energy that powers life on Earth is derived from the reaction in which oxygen combines with other substances. So we have a lot of the energy kind of that we have right now, that you have to undergo sometimes combustion, and when you are combusting, you are reacting with oxygen. So we have sulfur, selenium, tellurium. They are often referred to collectively as chalcogens, which is a Greek word, because most coppers all contain this element. So when you are mining copper, mostly you find these elements. It's sulfur. Mostly when you are doing mining, you see sulfur everywhere. Group 7, there are halogens, and there are fluorine, chlorine, bromine, iodine, astatine. So these groups are, astatine is, it's most of them are non-metals, or let's say all of them are non-metals. All exist as diatomic molecules. So they are, if you refer to the previous slide that we did on polyatomic molecules, you see that all of them are always in diatomic molecules. So these elements are among the most reactive elements, all combine violently with alkali metal to form salts such as NaCl. So they readily combine with metals, because the reason is that most of them, they are close to attaining octet. They are close to being stable. So they are looking for the elements that are ready to give them electrons so that they can be stable. For example, let's say chlorine. Chlorine is looking for an electron to be stable. So if it sees an element such as sodium that is ready to give the electron, it's going to react quickly with that element and be stable. So they are collectively known as halogen, which is from the Greek word has, which means salt, and gene, which means forming. And the last group is group 8A, which are the noble gases. They are the helium, neon, argon, krypton, xenon, and radon. They are collectively known as noble gases or inert gases, or sometimes they are also called rare gases. So they are the least reactive elements. From, as you can see from their names, all of them are in form of gas. So they are the least reactive elements of the period. And the reason why they are the least is because they are stable. When something is stable, you don't want to look for trouble. You are just stable. So they don't react easily. Though a report in 1962 was made where someone reacted xenon and fluorine together to produce that. But these are kind of reactions that don't just occur easily. They must have occurred in a very harsh kind of condition, because naturally these elements of group 8A, they're okay. They don't want to react. They just want to be on their own. So, like I said, that the elements that are in between Group 2A and Group 3A are the transitional elements. And they are the kind of elements that have variable oxidation states. We're going to get to that later. And we also have lanthanides and actinide series on the periodic table. And those are the blocks that you see under your periodic table. So transitional elements, we talked about that. So most occur naturally in combination with other elements, but we have few such as copper, silver, gold, and platinum. They are much less reactive, where they can be found in nature as pure elements. So they are much less reactive. So, like I said, under the block, you see that we have lactinide series and the actinide series. So lactinide series is a series with the elements that are in between lanthanum and hafnium, the periodic table. And the actinide series, they are the element between the actinium and rutherfordium. So learning check. So we are to identify each of the following elements as metal, non-metal, metalloid. So sodium is sodium metal or non-metal or metalloid. You have to identify. Please go back to the previous slide, pause this video, go back to your note, and try to figure out those questions. We have chlorine, silicon, iron, and carbon as well. Again, match the elements to this description. So metals in group 4A. So you have to find which of these sets belongs to group 4A. Non-metals in group 5A. Find metalloids in group 4A. These are tricky questions that you need to sit down and make sure that you figure them out on your own. So for library work, please find the usage of at least 2 elements from each group. These elements are not just there, we use them for something. So find their usage, at least 2 elements from each group. Find what do they use them for, what is the purpose of these elements. So we move further into the lecture where we're going to discuss periodic table trends and reactivity. So to discuss this trend and reactivity, we have some criteria to discuss, which are atomic radius, ionization energy, reactivity, electronegativity, and electron affinity. Please, I want your attention because you have to get it right from here. So we discussed the group first. So within a group, elements have the same number of valence electrons. Now, what do you mean by valence electron. I've said it earlier. The valence electron is the electron that is in the outermost shell of the atom. So for example, if you have lithium, lithium has atomic number of 3. So it has, that means it has 3 number of protons and also 3 number of electrons. So if you distribute lithium, lithium is going to be 2, 1. So that 1 is the valence electron that is in the outermost shell of, the atom. So, but as you go down the group, the number of shell increases. Yes. For example, let's take group 1 as an example. So if you move from hydrogen, which has just 1 shell, you go to lithium, lithium is going to have 2 shells. If you go to sodium, sodium is going to have 3 shells, and so on and so forth. So as you are going down the group, the number of shell is going to be increasing. So as the number of shell increases, the valence electron are moved further away from the nucleus. That is, the electron that is in the outermost shell of each atom, they are moving further away because the shells are growing bigger and bigger. So they are moving further away. Thus, it requires less energy to remove an electron from the outermost shell. The reason why it requires less energy is because those elements, those valence electrons at the outermost shell, they are far away from the nucleus. Remember, the nucleus contains the positively charged protons, and it is the positively charged proton that is attracting the electron to itself. So if you move far away, the force of attraction is going to be less. And that is why it is easy to lose those electrons in the outermost shell. And we'll get to that later. That's what we call ionization energy, because it's going to be low. The ionization energy is going to be low when it moves further. Okay, and it will also be more difficult to attract electrons. So if the shell is so big and you have your positive proton inside, it's also difficult for the protons inside to attract electron to itself because the electrons are far away. The shell is so big, so the electrons are far away. So that is for the group. Now, let's talk about the period. So within the period, elements have the same number of shells. Remember, for group, the reason why they belong to group 1, 2, or 3, or 4 is because they have the same number of electrons in the outermost shell. But for group, the group have the same number of shells. The shell don't change. For example, if let's talk about group period 2. So period 2 have 2 shells. That's what it means. Period 1 have 1 shells, 1 shell. Period 2 have 2 shells. Period 3, 3 shells, and so on and so forth. So within the period, the elements will have the same number of shells, but increase in the number of valence electrons. For example, let's for example, let's take period 2 as an example. In period 2, we have lithium, we have beryllium. Lithium is going to be 2, 1 when you distribute them into the shell, but beryllium is going to be 2, 2. That means as you are going across from left to right on the period, the number of valence electron is going to be increasing. So if you go to boron, we have 3, carbon we have 4, nitrogen we have 5, oxygen we have 6, fluorine we have 7. You see, so as you are moving from your left to the right, the valence electron, which is the number of electrons in the outermost shell, is going to be increasing. So as the number of protons and the valence electron increases, the attraction also increases. Why? Because the more negative charge you have and the more positive charge you have, the better attraction is going to be. So if you have a positive charge, a lot of positive charge in the nucleus, and you have also a lot of negative charge outside, then the attraction is going to be more. And that is why, let's read further. So the attraction increases, which pull the outermost shell close to the nucleus. See, so if you have a lot of protons, the positive charge in the nucleus, and you have so many electrons also outside, and what is going to happen is the positive in the nucleus is going to attract the the electron to itself. So that means it's you're going to be shrinking the shell. So as the electrons move to close to the nucleus, it requires more energy to take them away. So if you have so many protons in the nucleus attracting the electron to itself, it's going to take more energy to take it away from them because the attraction is so strong. So it's going to be difficult. And it will be easier for the atom to attract more electrons. Why? Because you have more protons in the nucleus. So if you have more protons in the nucleus, then you'll be able to attract more electrons to the center, to yourself. Okay, so that is the relationship on the period. Now, let's go into the specifics. Okay, before we go into the specific, let's also discuss the reactivity of metals. So as you go from the right to left, as you can see from the arrow, from right to left within a period, the amount of valence electron as metal has to give away decreases. Exactly. So if you are going from, let's take group, let's take period 2, for example. So that means if you are moving down from your fluorine down, the number of the valence electron is going to be decreasing. It's going to be decreasing. So that means, for example, fluorine has 7 electron in its outermost shell. So it's not going to give away 7. So it's not going to give away 7. But as you go down the period, the number of valence electron reduces, it decreases. So when it decreases, for example, let's say lithium. Lithium has just 1 electron. So it's easy, it can easily give away that 1 electron. It can easily give it away. So as you go down across from right to left within the period, the amount of valence electrons a metal has to give away, it decreases. For example, beryllium, we want to give away 2 electrons, but lithium, we want to give away 1. So it's become more readily available to react. So the less electrons that you want to give away, the better for you, because you're going to find someone who wants to react with you easily. Let's say for example, carbon that has 4, it's going to be difficult for carbon to see someone who wants to react with him, because carbon has 4. Carbon will not want to give away 4, and there is no element also that is ready to give carbon also 4 electrons. So it's difficult. But for example, sodium has 1 electron in its outermost shell. So it's easy for sodium to find someone who wants to take its 1 electron. And even sodium wants to give away that 1 electron. So sodium is fine with it. So as you go down the group, the valence electron moves farther away from the nucleus. Remember, we've discussed that earlier, which makes it easier to be taken away. So when you're going down the group, the shells are increasing, which means the electrons in the outermost shell, they can easily be given away. That means francium, if you check your periodic table, francium will be the most reactive metal. So let's go to non-metals. So as you go from left to right within the period, the atom is getting closer to obtain a full valence shell. What do we mean by that? So if we move from left to right, the atom is getting closer to be stable, to have 8 electrons in its outermost shell. And once they have 8, they are stable. So it is more readily to react to receive those electrons. So as you go up the group, the amount of shell an atom has decreases. So which pulls the valence electron in the outermost shell close to the nucleus. So if the number of shell that you have decreases, then it gives the proton in the nucleus more energy. It positions them in well so that they can attract something to them. They can attract the electron to them. So the atom's ability to attract more electron to the protons in the nucleus, because there are fewer shells. There are fewer shells. If you are going from bottom to up the group, there are fewer shells. For example, sodium will have 3 shells, but lithium is going to have 1 shell, 2 shells. I beg your pardon. That means lithium, the protons in the lithium can easily attract electrons to them because there are not so many shells surrounding them. So by the virtue of that, that means that fluorine is going to be most reactive non-metal. Take note of that. So let's go into the specifics now. Let's talk about atomic radius. Atomic radius is the measure of how large the atom is. From this definition, you of course can guess how large an atom can be. And it's going to be in terms of the shells that they have. The more shells you have, the bigger it is. So you measure from the nucleus to the atom's energy level. And how does atomic radius change down the group? So it increases down the group, of course. So lithium, we have 2 shells, and sodium is going to have 3, and potassium is going to have 4. So as you are going down the group, the shells are becoming bigger. That means bigger the bigger the atomic radius is going to be. That's just a straightforward explanation for that. So when you had energy level every time you had energy level every time you move down the group, and also the energy level means that you have more electrons and you have a larger atoms. So how does the atomic radius change now across the group? So it's going to decrease across the group. And what is the why? Why is it going to decrease across the group? Is because when you are moving across the group, that means from left to right, it means that you're going to start having more protons in the nucleus. And the more protons that you have in the nucleus, the better the attraction is going to be. So if you have so many protons in the nucleus and you have electrons surrounding it, the proton in the nucleus, which is positive, is going to attract the negative electrons surrounding it. And when that attraction is so much, it's going to decrease the atomic radius. And that is why as we are moving across, it's going to be decreasing across the period. So the more protons in the nucleus, the higher the electrical force pulls the electrons to the nucleus, and that makes it decrease. So ionization energy, it's another one that we're going to look at. What is ionization energy? Ionization energy is the amount of energy needed to remove an electron from an atom. You see, before you can understand the trend, you need to understand the yardstick that you're using. So you need an energy to remove an electron from an atom. Let's see how it is in terms of the trend on the periodic table. So ionization energy, how does it change down a group? So ionization energy decreases as you go down a group. It decreases as you go down a group. Remember, ionization energy is the energy needed to remove an electron from the from an atom. So this energy decreases as you go down the group. That means that, for example, if you have sodium, which has 1 electron in its outermost shell, it's going to be a little bit difficult for you to take that 1 electron away because the electron is closer to the nucleus. Remember, the nucleus, which is positively charged, is attracting the electron so much. But as you go down the group, as you go to potassium, you see the shell becomes bigger. And when the shell becomes bigger, the farther the valence electron to the nucleus. So the farther the valence electron to the nucleus, the easier for those electrons to be lost or to be taken away by another atom. So that's why when you go down the group, the ionization energy is going to decrease because those electrons in the outermost shell, it requires less energy to take them away because they are far away. They are so far away from the nucleus, which is holding them together. So the size of the atom increases, and when it increases, the electron is farther away from the nucleus. Just explain that. So little attraction between the nucleus and the electrons. So how does it change across a period? So ionization energy increase as you move from left to right across the period. I think we should be able to guess why it's moving like that before we even go to the slide. You see? So if you are moving from left to right, that means you're going to have, remember from the previous slide, we're going to have more protons, more positively charged protons in the nucleus, and which means more attraction. So it's going to be attracting them. It's going to be attracting them. So if you have a stronger attraction now, then that means you're going to need a lot of energy before you can remove those electrons away because you have a greater attraction. So the harder to get away because there are lots of attraction between the positive charged protons and these electrons that are revolving around the nucleus when you move across the period from left to right. So the nuclear charge protons increases while shielding the electrons in the lower in the lower EL energy level is also constant. It's constant. So let's move to electronegativity. Electronegativity is the ability of an atom to attract an electron. So if you want to be stable, you want to attract the electron to yourself. So what do you have the ability to attract that electron to yourself? That is what electronegativity is talking about. So the trends in electronegativity on the periodic table, electronegativity generally decreases as you move down a group, as you move down a group. So why? Because electrons farther away from the nucleus and the weaker the attraction. You see, when you begin to move down the group, the shell, remember, the shell are becoming bigger. And when they are becoming bigger, the nucleus that has the positive charge that wants to attract electron, it's farther away from the nucleus that it's farther away from the electron that it want to attract. So when the shell is becoming bigger, the electron, the proton inside the nucleus is farther away from the electron. So it's difficult for the proton to attract the electron to itself. And that's what we call electronegativity. Do you have the ability to attract an electron to yourself? The answer is, do you have a bigger shell? If you have a bigger shell, the proton that is going to help you to attract, which is positively charged, is farther away from the nucleus, from the electrons. So it's going to be difficult for the protons to attract the electron to itself. So for the group, for the period now, electronegativity increases as you move across the period, as you move from left to right. And we can also guess why. Because in the nucleus, as you move across from left to right, the proton in the nucleus increases. So if the protons increases, that means you are increasing the positive charge of the nucleus. And the more positive charge you have, the better attraction you're going to have because unlike charges attract themselves. So the positive, we want to attract the negative. Any electron that it sees, we want to attract. And that's why the electronegativity is going to increase as you move from left to right on the periodic table. So they are getting closer to the octet, they have more protons, and they can easily attract electrons. So the last one is electron affinity. So electron affinity is the energy change that occurs as an atom gains electron. Remember, for an atom to gain electron, it must have what? Electronegativity. So if electronegativity is the ability for the atom to attract the electron to itself. So what is the energy that is gained there? You can see that the trend is, can say similar to the electronegativity. So electron affinity increases across the periodic table. So that means when you are moving from left to right, you're going to have more positive protons in the nucleus. And that means that the positive protons can attract more electrons, the negative electrons, to itself. That's why it increases across the periodic table from left to right due to the nuclear charge in the nucleus. Okay, so it also decreases, I beg your pardon, it increases from bottom to top in the periodic table due to atomic size. We can also explain that. We're talking about the group now. So the arrow that moves from bottom to top for the group, you can see that the electron affinity is going to increase as you move from bottom to top. So the reason is also clear that we've explained earlier is because at the bottom there are so many shells. There are so many shells, so it's difficult for the protons to attract electron to itself because there are so many shells. But as you go from bottom to top, the shells are reducing. And when they are reducing, the proton inside will have better chance to attract electrons to itself. And the more electron they attract, the more energy that they're going to have, which is the electron affinity. So let's do some learning check. Which metal is more reactive? So you need to go back to what we've explained on the trend and see, try and answer that. The next one, learning check. So which metal is more reactive? You also have to go back and check the trend that we've discussed earlier. And which non-metal is more reactive? Remember, we discussed metals and we discussed non-metals. So which of these non-metal is more reactive? Then which of these non-metal is also more reactive? So library work, please read about the trend on the periodic table with respect to ionization energy, electronegativity, and electron affinity. As you can see, there are similarities for this trend. So just try and figure them out and try to master them. This will be the end of lecture 1. See you for lecture 2.